5.4, so we're going to finish up our lesson here, and this will finish up chapter 5 content. So the graph of an nth degree polynomial function has at most n x-intercepts, okay? And at most n minus 1 turning points, okay? So let me try to explain this with some examples of some graphs. So say I have some polynomial function, x cubed minus 2x squared minus x plus 1. Now, the degree of f here, looking at the largest term, it's a degree 3. So the degree of f is equal to 3. Okay, so what is this telling me? We have at most 3 x-intercepts. Okay, at most 3 x-intercepts. So with this graph here, this graph kind of looks something like this here. Okay, so what's happening here? I'm actually crossing the axis 1, 2, 3 places, okay? At most 3. I can't cross it more than 3 times. Now, if I look at this graph, okay, if this were to shift down a little bit or to shift up a little bit, what would happen? I go from having 3 intercepts to looks like just 1 intercept, right? So it is possible to have 1 intercept, 1 x-intercept, okay? But it's also possible if I just had 2 intercepts, right? Maybe it touches right here and right here, okay? So you could have 2 x-intercepts. This doesn't contradict at most 3. If I say I have at most $3 in my pocket, maybe I got $3, maybe I got $2, maybe I have 1. Those are all okay. That's at most 3. So be careful when you see at most n intercepts. It's not saying that because it's degree 3 that there has to be 3 intercepts. It's just saying that the most intercepts you can have are 3 intercepts. You could just have 1, could have 2, but at most 3. Okay? Now, for cubic is different because I know one side is going to positive infinity and the other side's got to go to negative infinity. So I'm guaranteed at least 1. But just because I say at most 3, I mean, technically, like if it was an even degree, like here's another example, x to the 4th minus 2x cubed plus 1, okay? This graph looks something weird like this, all right? Now, when I look at this, I see 1, 2 intercepts. So the degree for this one, this is a degree 4 polynomial, okay? A degree 4 polynomial. Now, so maybe that's some g of x, right? Okay, so that's a degree 4. So this has 2 x-intercepts, but it has at most 4. So 2 satisfies at most 4, okay? But technically, I could have a situation where there were none, right? So if this was above the x-axis, then it never crosses, okay? So technically you could have a scenario where there were none, and that would be at most 4. So that happens whenever your degree is even, okay? You could have a possibility of no x-intercept. But if the degree is odd, that means the end behavior is the opposite. So there's this theorem called an intermediate value theorem. Basically, it says, like, if I go from here, a negative number to a positive number, at some point, I have to cross 0. Okay, that's what the intermediate value theorem says. So there has to be at least one solution. You all don't need to know that. I'm just telling you some technicalities. Okay, so The other part of this little theorem is that not only is there at most n intercepts, but there's at most n minus 1 turns. So what is a turn? So a turn in the graph, meaning like we're going from increasing to decreasing, or we're going from decreasing to increasing. Our function is changing direction. The monotonicity is changing. It's going from increasing to decreasing. Okay? So, how many turns do we have with this? Well, it looks like we're going up, 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 up. And then what are we doing? We make a turn and we go down, 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 down. So that's one turn. And then we go up, 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 up. So there's my second turn right there. So how do I know? Well, the degree is 3, and remember it was n minus 1 turning points, right? So that's 3 minus 1 equal to 2 turns. Right, so we turn at most 2 times, and we did turn 2 times. Now with this one, the second example, what am I doing? I'm going down, 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 and then what do? So right here, I turn from going down, and I turn into going up, 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 up. So there's only one turn here, but the at most part, it says at most n minus 1. Well, n here is 4, degree 4. So it has at most 3, okay? Now we know looking at the graph that there's only one term, but that satisfies at most 3, okay? There's one more example, and I've got a graph here, and this is x minus 1 all cubed. So this is the cubic graph, okay, the cubic graph, but the x minus 1 inside shifts it which way? Shifts it to the right. How far? 1 unit. So I take my graph and I shift it to the right 1 unit. So this is 1 comma 0. Okay? When I look at this, all right, a cubic, so maybe some cubic here, that has a degree 3. So what does that tell me? At most 3, what? At most 3 X-Intercepts, okay? For this particular one, there's only one X-Intercept, okay? It's just this one right here. The multiplicity is 3, all right? There's 3 copies of it. But there's also at most, well, 3 minus 1, 2 turning points. But when I look at this graph, it looks like it's always going up. So are there any turning points in reality? There are no turning points. So you can have a graph that has no turning points, and it's still okay. It says at most 2. So if you say I've got at most $2 in my pocket and you've only got no dollars, that's okay. You didn't lie, right? I've got at most $1 million in my bank account, except my bank account is 0. Oh, man. Right? So technically, you're not lying, right? When you say at most. Okay, I want you to think about this, though. Let's think more about this h of x, x minus 1 cubed. I hinted a little bit. This multiplicity, the multiplicity here is equal to 3. That multiplicity is odd, first of all. It's an odd multiplicity. So odd tells me what? It tells me that it crosses. So I cross the axis. So let's zoom in a little bit here. But when I cross the axis, I don't just go straight through it. I actually have a little bit of a bend, okay? So there's a little bit of a bend there going through. And why do I have that bend? It flattens out. It flattens out. Why does it flatten out? It flattens out because the multiplicity is greater than 1. Okay, it's greater than 1. That multiplicity is 3 there. So it actually flattens out. You think about it, if you're comparing it maybe with like a line. So maybe the line is like x minus 1. Okay, so I take a graph x minus 1. This has a multiplicity of 1. There's no bending at all. It passes through 1. But when you look at the cubic graph, when it comes in, okay, it's coming in hot, and then it slows down, and then it speeds up and it shoots off, okay? What's happening as it gets close to the solution x equal to 1? Well, it's actually flattening out, okay? It's flattening out. It's not coming in straight like that black curve comes in straight, right? It's flattening out and it's curving in to this solution here. Okay, so that's why you see that little bend there when you're talking about a cubic, okay, x minus 1 cubed versus some line that just passes straight through, like an x minus 1 to the 1. The multiplicity, the higher the power, right, the higher the power, the more flatten out we get around the solution. So if this was like an x minus 1 to the 5th, okay? So that's kind of how that works, all right? So just to summarize what we've been talking about here, because it can be a little bit confusing. Odd multiplicity, okay? If I have an odd multiplicity, multiplicity 1, multiplicity 3, multiplicity 5, then we cross through the x-axis. Okay, so example, I'm going to cut through the x-axis just like that. Okay, if it's an even multiplicity, I'm going to touch the x-axis. I'm going to touch the x-axis. So what does that look like? I come down, I touch it, and then I go right back off. Okay, kind of like a parabola. All right, it's an even multiplicity. Now the multiplicity, this is the number of values for which a given condition holds true. Okay? I think of multiplicity as how many copies I have, okay, of some factor. So I just think of it as how many copies I have. And if my multiplicity, if the multiplicity is bigger than 1, then the 0 flattens out. Okay, so you're going to have questions that say, does the 0 flatten out? You look at the multiplicity, okay? So this last problem here is going to summarize what we've done, okay? So I want to sketch. Oh my goodness. I'm going to spell that right at some point. Sketch the graph of f of x equal to x plus 2 times x plus 1 squared times x minus 3 cubed. Okay? In behavior. In behavior. I want to know the in behavior. I want to know the X-intercepts. I want to know Y-intercept. Okay? So first thing I need to do to get in behavior is I need to be able to look at the an x to the n term. That dominant term there. The leading term. So you either have to multiply this whole thing out, which you can do, but it's very challenging, or you can look at the highest degree term in each parentheses. The highest degree term is a 1x. How many of them are there? There's just one of them. So I have 1x raised to the 1. The highest degree term is an x, and how many do I have? I got 2 of them. So I have this 1x raised to the 2. The highest degree term is another 1x. How many do I have? I got 3 of them. Now I'll multiply all those together. And when I multiply together, I have x to the 1 times x squared times x cubed. This is x to the 6th. Okay? So my lead term, that's 1x to the 6th. So what do I know? What do I know? Well, I know that it's even degree, so they're either both positive infinity or both negative infinity for the end behavior. I look at the coefficient. The coefficient's positive. When I'm positive, I'm going up both ways. When I'm negative, I'm going down to negative infinity both ways. So I know the end behavior agrees and they're both positive infinity. Now I just got to figure out how does it behave in between. Well, let's study the pieces. Okay, let's study the different pieces here. So I've got 3 pieces going on. So let's see if we can't work through it. So set them equal to 0. So to get the x-intercept, set y equal to 0. Y is f of x. So if 0 equals x plus 2 times x plus 1 squared times x minus 3 cubed, okay, that means that x plus 2 equals 0. So x is negative 2. X plus 1 all squared equal to 0 tells me if I take the square root of both sides, I get x plus 1 equal to 0. So x is equal to negative 1. And then this last one, if I solve it, what makes that 0? Well, if I plug in, let's see, if I plug in a 3, that would make that 0. So x equals 3 is another one. So those are my 3 zeros, okay? If you're having trouble with that last one, x minus 3 cubed equal to 0. Cube root both sides, cube root of 0 is 0. I have x minus 3 equal to 0. And so add 3, I get x equals 3. All right? So that's what I did right there. Okay, so I know 3 is a 0. I know negative 1 is a 0. And I know negative 2 is a 0. Okay, how do I get y-intercepts? How do I get the y-intercept? I set x equal to 0. So everywhere I see an x, I'm going to put a 0. So f of 0 equals 0 plus 2 to the 1, 0 plus 1 to the 2, and 0 minus 3 to the 3. So that's 2 times 1 squared times negative 3 cubed. So 1 squared is just 1, so that's 2 times negative, negative, negative is a negative 27. So that's negative 54. So I know I'm going to cross down here at negative 54. Okay, we don't have to have it perfect. We're just trying to draw it in. All right. So look at the multiplicities. Okay, so let me copy this. we'll talk about the multiplicities for each. Okay, so this one has a multiplicity equal to 1. So we cross, it's odd multiplicity, we cross in no flatten out. So it's not greater than 1 multiplicity, so we don't flatten out. So whenever I have my x equal to -2 for that 0, I cross, but I don't flatten out. So I'm coming down, and I cross, and I don't flatten out. Okay, for this next one, for the 0 of x equals -1, my multiplicity, I'll look at how many, there's 2, so the multiplicity is equal to 2. 2 is even, so I touch. 2 is greater than 1, so I do flatten out. Okay, so I flatten out and I touch. Okay, so I'm going to come in here. I'm going to flatten out. When I get close to here, I'm going to touch the graph, and then I'm going to go back down, and I'm going to go through this point here. Remember, I don't care where the hump is. That's calculus that tells me where the hump is. You just cross through that intercept there, okay? Now I need to figure out, am I going to cross straight through, or am I going to bend and go through? How do I do that? And how do I know I'm going to cut through? Well, because my end behavior is positive infinity, so I know I got to cut through. I'm not going to bounce and go down, okay? So look at this last one. This is my x equal 3 root. The multiplicity here is equal to 3. Okay, so the multiplicity there is equal to 3. So that's odd. That tells me that I cross. Okay, I knew I was going to cross. I just didn't know if I flattened out or not. But I do flatten out. Why do I flatten out? The multiplicity is greater than 1. Therefore, I flatten out. So what does that mean? That means as I get closer and closer here, I flatten out. I kind of make a little bit of a wiggle going through just like that, and then up. Okay? So that summarizes, so I'll give you a full picture of what's going on there. That summarizes everything, and that's a crucial part to your next test, knowing how to do this part. Okay, guys, good luck.